Are we just done now? We're done. Okay, 37. Let A, B, and C form a permanent Pythagorean triple. Show that one of A or B is a multiple of 3. Okay, so show 3 divides A or 3 divides B. Why must this be true? I think the way I did it, I did sort of use number 35. Let's see, what did I do? I said, since we now know what we know from the previous problem, specifically 36, without loss of generality, let A be odd, B even, and C odd. Well, if that's the case, then take C squared. It must be 4k squared plus 4k plus 1. Well, that can be rewritten as 3k squared plus 3k plus k squared plus k plus 1. I think this is what I did. For some reason, I thought to do this. And so this is just a multiple of 3 plus k plus 1 plus 1. Does this make any sense?
Yeah.
I can't understand what I actually did, but I know that k plus 1 is always congruent to either 0 or 2 mod 3. Why is that helpful?
Then C squared is either like 0 or 1, but this is, that's just unnecessary in all the ways. Because you don't even need C to be odd or anything. Like just do it straight out.
Yeah, it is faster if you just do it. Can I just like stop? I'm just like tired. I don't want to do this problem. I think it's like not that hard. You just do it. The most straightforward way is to just do it. We're trying to show that one of them must be a multiple of 3. If we just suppose they're both not. If you take something which is not a multiple of 3, have we already shown this? If neither of them is, then A is either 3k plus 1 or A is in the form of 3k plus 2. And when you square, you get that this is 9k squared plus 6k plus 1, and this is 9k squared plus 12k plus 4. So either way, the square is going to be, A squared is going to be 1 mod 3. And here also, right? So if that's true, if a non-multiple of 3 squared is 1 mod 3, then if they're both, if I need to prove that one of them is a multiple of 3, then imagine that neither of them are. If neither of them are, then A squared plus B squared would have to be congruent to 2 mod 3. But that is impossible because, why is that impossible?
Because C is also a number. No squared number is 2 mod 3.
Oh yeah, by the same reason.
Yeah.
Okay, so basically the talking it out way is, dude, when you square an odd number, you just get always 1 mod 3.
Or 0 if you're already divisible by 3.
Right. But a non-multiple of 3,
So you need it for C. Like, it's never 2. It's just never 2. That's it.
it's never 2. An odd squared, oh yeah, sorry. So also true is that an odd squared, C has to be odd, and an odd squared is also congruent to,
Either 0 or 1. You don't need it to be odd or anything.
well, I know that C is odd though.
You don't, like, it's just unnecessary information.
Really?
Yes.
Yes. Yes. Yes. Okay, so yeah, this is 4k squared plus, so you just never get, and just a number squared is just never
2 mod 3.
2 mod 3. Yet A squared plus B squared is 2 mod 3. That's really that's the whole proof. We feeling good? Or not good? Bong, you good?
Yeah.
Okay, good. No second, let's erase the board. Let's do one page from the packet. Should we do the page that caused us to erupt into controversy? Do we have time for this? Yeah, sure we do.
Be able to erase as much more effectively.
Go, man. No, it's you just have to go slow and careful. It takes a good 20 seconds. Oh, it's just not working. Alright. Okay, good. 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 Okay, so I don't know if any of you put a lot more mental effort into this, but the hardest pages of the packet I thought were 3, 5, and 6. In particular, mathematical induction implies complete induction is quite hard. And so, what are we actually trying to prove when we're trying to prove that mathematical induction implies complete induction? Well, we are trying to prove that for all possible properties, if I know that the property is true of 0, and I know that for any k, when the property is true of k, that it's true of k plus 1. If that proves to me that it's true for all numbers, so that is mathematical induction. It's the power to conclude that every number has a certain property after establishing that 0 has the property and the property is always inherited. I need to show that this power can be used to prove another power. The power for any possible property P to conclude after knowing that the property is true of 0 and that the property is true of all the numbers up to P of k, if from this I can conclude P of k plus 1, just going off the frame, if that is the case, then I can conclude that it's true for all numbers. That is complete induction. Okay, so the logical structure here is I assume mathematical induction, and now I tried to prove complete induction. Alright, how do I prove complete induction? I take arbitrary property P, and now I need to prove that about this property. That if I know it's true of 0, and I know that whenever it's true of all the numbers up to a certain point, then it's true of the next number, then it will be true for all numbers. Okay, so that is what I'm going to assume right now. I will assume that I have the things that I need in order to conclude that complete induction. So I will assume that I have P of 0, and that I have that for any possible k, when it's true of 0, and it's true of 1, and it's true of all the numbers up to k, that from this, I can conclude P of k plus 1. And then somehow using this, I'm going to prove that everything has a certain property. Okay. Everyone good with me, logically speaking? Good. Okay. Why is this true? Well, I only have mathematical induction to work with. And so this is, mathematical induction is like not strong enough to get me where I need to go. And I think some of you kind of started thinking, eventually you figured this out once you sort of wrote it out in this level of detail. If I try innocently, I'll write some crap now in red. If I try innocently to just apply mathematical induction, well, mathematical induction says that if I can prove that, like, okay, if I want to use mathematical induction, then I need to establish that it's always inherited by the next number. But I have no way of doing this, right? Because if I only know P of k, I can't conclude P of k plus 1. This is a statement that I actually have to prove. This is what I would have to prove to enable to get my prize, which is the consequent. I have to prove this antecedent. That's how regular mathematical induction works. But to prove this antecedent, I have to show that the property is always inherited. But how can I show that the property is always inherited when the only thing I know is that if all the numbers up to the point, the property is inherited? Okay, so there's a trick. Did you guys figure it out or look it up?
No.
Oh, no one did. Very
I don't know, I feel
exciting.
like I got it, but wait, don't you were right when you said you have to kind of use the well-ordering principle.
No, I said that you have to use induction on the inside. I'm not sure. That was a guess.
Okay, here's what you do. You define a new property.
Yeah, okay, that's what it is.
So let Q of M be simply the property of it holding for all the numbers up to M.
Oh.
Wait, I did something different.
Definition. That is a legit property, right? It's a property called Q. It is the property of it being true for all the numbers from 0 to M. No one said that this property has to be the same as that property. And so I know mathematical induction. Mathematical induction is the power to apply mathematical induction to any arbitrary property. So I'm going to apply mathematical induction to property Q. And mathematical induction says I can prove that everything has property Q by verifying that these sort of things hold. So first of all, I know P of 0. Okay, just watch. So P of 0 is true because I've assumed it, right? So since P of 0, do you agree that Q of 0 holds?
Yes.
Okay, cool. So now I have Q of 0. Well, in preparation to apply mathematical induction for Q, on Q, I need to show that the Q property is always inherited, right? So my plan now is to show that for all K, that Q of K implies Q of K plus 1.
Wait, why is it useful to know that?
Wait, just watch me, watch this. I'm gonna show this, even if you don't see why yet. Let me just like do it. Okay, well, it's actually like relatively straightforward, right? Because to prove this, what must I do? I must take an arbitrary K, suppose Q of K, and then establish Q of K plus 1. Right? Well, what is Q of K by definition? Suppose. Q of K just is the statement P of 0 and P of 1 and all the way up to P of K. Agreed? But I have the assumption that one uses when one, I have like this, basically, right? So since I know this, since it's true that P of 0 and P of 1 and all the way up to P of K implies P of K plus 1, then my assumption of Q of K just gives me this antecedent. And so now I just have P of K plus 1. But Q of K together with P of K plus 1 just leads to Q of K plus 1. Now cool? So I've showed that on the assumption that, in words, what I've basically done is to say, okay, suppose it's true for all the numbers up to that point. Well, then it's true of the next one. But I only had to use mathematical induction because my property was the property of it being true for all of them up to that point. Okay. Eric's excited. So now what have I showed? I have showed, so what I now currently have, I have Q of 0, and I have that for any K, Q of K implies Q of K plus 1. And since I have that, I'm entitled by the property of mathematical induction, which I have in my pocket, to conclude that for all n Q of n. But if this is true for all the numbers, if it's all up to Q of n, then it's certainly true that it's all that the P, so I can go into more detail on that last step, but it's definitely true for every possible number since it's true for all the numbers up to every single possible number.
So I guess you could just say like, take an arbitrary
Take an arbitrary n.
Okay.
It's true for all the numbers up to n, including n. So it is in particular it's true of n, so it's true for all n.
George, can I show you?
Alright, cool. You don't seem impressed. You seem, Eric, are you impressed? I know he's giggling over there. Alright, cool.
I was close, but I defined Q to be P of n implies P of n plus 1.
I don't know of any other way to do this. I feel like this is like the way to do
And
it.
this is the way to do it.
Yeah, I think this is like the way to do it.
I tried to put induction inside
Good.
induction.
I don't know. I don't think I came up with this either. I think like, Ethan Holland did or something. Like maybe it was even the year before that. Yeah, I think it was like.
Proof by contradiction not possible?
I don't know. I will be happy to look at your proofs later. I don't know. This is the elegant proof. There might be other proofs. I think when you did my work too, it's just like you just kind of brute forced it out with a bunch of cases. But I think every time, I guess George, I looked at George's proof. Every time you have a proof, every time your proof involves like a bunch of dots, you're sort of.
You're like, no, it was saying that it was kind of induction, but
Yeah.
a finite number of cases.
I don't know. I would show it to someone smart and patient and
No, but it
critical
still
and
is
loving.
induction.
I think it's still induction if you have a dot. I know I have some dots, but they're like formula dots. They're not like step dots.
No, because like induction is a finite number of cases.
Also.
Also.
Yeah.
So you can't just say that.
Yeah. That's kind of that's the thing. All right. Good. Good. Shall we have a quiz?
Is that?
It's like pretty
Can I
chill.
have like a minute to copy this?
You can have a minute to copy this. Then please, I'm gonna turn this off. Were we even remotely in frame? Oh yeah, we kind of were.
We're slightly out of frame there, but